We'll skip the title. So this is me. I'm ALQ on Twitter. So if you have anything, any comments, questions, please let me know. Also, if you have any comments or questions during the talk, fire away, because I want to have it as interactive as possible. So what I figured we'd talk about tonight is a few things. So first of all, and that's not going to be product, not a product pitch, but just explain what the problem space is, what it is that we're dealing with. So what do we do, and who is the user of Datadog. Then from there, we'll go into a little bit of domain constraints. So based on what the problem space is, what constraints it entails, and what constraints it doesn't entail, so what kind of trade-offs you can make. Then we'll look at the data model, not obviously the actual objects we're using or the data structures we use, but more the way we can represent the problem. Access patterns, which basically is how do we access the data, or how our users access the data, which then we'll get to a presentation of our architecture, which is by and large a really iterative architecture. So it took us a few years to get there. Not designed to be authoritative or anything like that. Also look at the tools that we use, data stores, languages, libraries, and so on and so forth. And last, a few challenges that we face. So we'll kind of discuss a few technical challenges, that is. Okay, so what Datadog is it's infrastructure monitoring as a service. So it's a monitoring tool, and so who here uses a monitoring tool, as an infrastructure monitoring tool? Okay, so maybe a third of the audience. So it's something that watches performance metrics coming from that kind of tools. So anything from databases, web front ends, load balancers, web tiers, application servers. It's even bare metal, AWS or and so on and so forth. So the idea is that you have one place, because your application is typically built on top of a bunch of these components, is you have one place where you can see how the app is performing. So far so good? All right. Now, so what is really monitoring at a highest level? What does it mean? So really, it's a tool, it's a system, it's whatever you've installed, it's whatever wakes you up at night when something goes wrong. But really, it's the primary interface you have to understand your application. So if you're running an app, if it's non-trivial, if it's just distributed application, you'll end up having something that tells you how well it's doing, where it's failing, the bottlenecks, and so on. And that's your monitoring system. So it's the primary interface where you can learn and understand how your system is doing. You can't, if you have a data center, you can't just go walk in the data center, look at the racks, and kind of understand what's happening, obviously. So you need something to mediate that, and that is, in essence, your monitoring system. Now, in the worst cases, your monitoring system is your customers, because basically they tell you when something goes wrong and you fix it. That's not it's one way to do it. It's not the way I'd recommend, but it's been done in the past. In the better cases, you have something that kind of sucks performance metrics all the time, around the clock from your various components, from your software, and tells you, hey, this is going well. This is, there's a problem here. But that's essentially what it is. Two quick taxonomy about metrics. So the monitoring system, what it consumes first and foremost is metrics. And metrics, so an example of a metric is, for instance, at the lowest level could be how much CPU a particular machine is, or how busy is the CPU in a given machine. At the highest level, it could be how many users are on the site at a given time. So it really varies. The taxonomy is relatively simple, though. So you have, in terms of metrics that you're going to care about, it's either about resource or workload. So resource metrics is stuff you consume. So it could be CPU, network, memory, storage, and so on. And workload is what you produce, what your application, what it is that you're running on the box is producing, or the application as a whole is producing. And really, to understand how things are going, how your application, your system is performing, and that, by the way, applies to, it could be a factory, it could be anything. If in the case of a factory, you have you get stuff in, you produce widgets, and your workload is how many widgets you produce an hour. So that's a physical work. in our world, the software world, so resources typically, with the machines, the resource of the machine, and workload is, whatever it is that you're producing. So this taxonomy applies kind of regardless of the application that you've written or you use, and that's going to be, that's one way to look at the metrics. And so the monitoring system will first and foremost consume these metrics and make some judgment or display them, make some judgment about whether they're good or bad, if you will. So far so good? Questions? All right. Now concretely speaking, now in the case, I took some screenshots on it, so that's the product page part of the presentation. When you use the monitoring system, first and foremost, you're basically graphing a lot of stuff. So this is one example. And the idea is that you're not graphing because you like colors and you like stuff that moves and it's cool. You're graphing because really quickly, you can see interesting patterns. Here and there are different metrics, but they exhibit the same pattern. Whether it's kind of flat, or whether it's getting bad here, or so whether there's a spike here. So the brain is amazingly good at figuring out patterns. And that's why a lot of the monitoring tools now offer, including Datadog, a really rich graphing library. So the idea is that, let's walk through an example of monitoring. So I have here two metrics, one of throughput and one of contention. So it could be throughput of anything, it could be number of pages served or whatever, number of people walking the subway in a given station. And contention is so the measure of how many unique things are in contention are consumed. And so the typical, the way you can use a monitoring system is, so you have these two metrics. You have an intuition, or from experience, you understand that there's some kind of relationship between both. And what you want to be able to do is you want to be able to, with your monitoring system, so formulate a hypothesis with a few keystrokes, transform the data a little bit so that you can identify patterns much faster. And so in this case, if you take the derivative of both metrics, in this case, if you sum everything, take the derivative, and here take the derivative, the first derivative, you can see that there's some kind of correlation between contention and throughput, which, by the way, you could kind of figure out if you have contention on something, for instance, turnstiles in a subway station, the number of people entering a subway station is gonna decrease. So that's a quick example of using a monitoring system. Now, so it's really about getting a quick feedback loop, being able to understand what your application is doing, and be able to play with the data, slice and dice, to transform in a way that you can quickly validate hypotheses. Does that make sense? I see people frown. Yeah, go ahead.
What data would grab that contention graph?
So this in particular is the number of locks in a relational database. So in that, it could be anything, but in this case, that's what it is. And that application, the throughput of that application depends on that relational database. And so whenever it starts to lock up, everybody in that application starts to wait for for their turn to grab the lock, or the locks, as it were. Cool. All right. So the second thing, so you do graphing and you manipulate the data. The second thing you want to do with the monitoring system is you do a lot of alerting. And alerting is really anomaly detection because you don't have time to watch 1,000 metrics. So that's define alerts, threshold. You can do a number of different things. But that's the other thing. Another very common use case of monitoring. And the third use case is more of what I would call team sport, is that whenever you have a complex application, you need to be able to talk about the data. You have a lot of back and forth. So this is, for instance, one discussion we had on a particular metric that's kind of actually talking about the same problem. So that's really the main three use cases of a monitoring system. So you do a lot of graphing. It's real time, of course. Hence the title of the talk. It is you graph, you do a lot of graphing, you want to alert on the metrics, and then you do a lot of collaboration around the data to try to really understand what the application is doing. Because if you just look at the architecture diagram, you don't really understand much. That's the sad truth. So Knowing that that's the problem space. That's the use cases, if you will. So the highest level of the description of the problem. So what kind of constraints does that entail? And the idea again is that we start from kind of the highest level use cases, and we look at the constraints, and then it tells us what kind of trade-offs we can do, and then that's going to help us get to some architecture. So the main constraints, the first one is latency. So when I mean real time, there's a lot of understanding of real time. I mean real time in the sense that this is a 10 to 30 second latency between the time you collect a given metric, for instance, how much CPU a machine is using, to the time you can see it on a graph. So it's 10 to 30 seconds. It's typically within 10 to 30 seconds. There's a number of factors. It could be 1 second or half a second. There's a number of factors that play there. It could be time it takes to send the data and time it takes to process it, and so on and so forth. The interesting thing is that, so it's really time to signal, so time from the moment you collect, there's a program somewhere that collects the metric to the time you receive it, and your brain can do something with it. It's not really page load, so the pages load faster than that, hopefully, but that's one key thing. So the idea is that so it's not 200 milliseconds, it's not 1 microsecond. And because for this particular domain, you're not going to be able to react to, there's a CPU spike of a microsecond, because what are you going to do? There's nothing actionable there. It's also not 10 minutes in the sense that you don't want to find out, you don't want your customers to call you and say, hey, the website is slow. And because in 10 minutes they can figure out that there's a problem. So that's where 10 to 30 seconds kind of maps to how fast somebody and people can look at the graph, grok it, and then react on it. So that's first constraint. Second constraint is its availability. I mean, that's kind of standard, but in this case, we get data when you run a monitoring service. You get data 24/7, 365, blah blah blah. There's no seasonality because it's just machines talking to other machines. So it's Thanksgiving, it'll be as busy as tomorrow at noon. It doesn't really matter. It just increases ever so slowly as we have more users, more machines reporting to the system. And the third key constraint is that you want to have access control, and that's very generic to any multi-tenanted system. So if you run something as a service, usually you'll have all your data in one place, but you have multiple users that don't necessarily want to see each other's data. So in our case, that means obviously that the data that we receive has to be partitioned by account. So now let's look at degrees of freedom, and I'll try to make it, as the talk advances, it gets more and more concrete. So fear not. So degrees of freedom, what kind of trade-offs you can make. I talked a little bit about the 100 millisecond round trip. I don't care if it takes 50 milliseconds between the time I gather a metric on a machine and the time I can see it, because if it takes 2 seconds, it'll be the same result. There's not a time. So there's no point in over-engineering to get like super fast latency. So this is not a financial trading application. This is really monitoring infrastructure. So that's we can get away with that. The second thing is we don't have to engineer for crazy elasticity. Certain bursts, Black Friday, Cyber Monday, etc., etc. That's not, we don't really care. In our case, what really drives the amount of volume of data, the volume of data we get is how many customers or how many users connect their machines to Datadog, so you can start streaming metrics to us. Now, the third one we can get away with to some extent is precision, and that's an interesting one. So precision kind of acts as a counterbalance, or not a counterbalance, but can be antagonistic with latency. So here you have essentially the same metric in two different configurations. One where it's very precise, that is to say you have a lot of data points, and so you can see it's kind of more jagged, etc. The problem is it's late. So I mean the x-axis, which is time, doesn't really matter what it is, but the actual scale. But it's not very useful because here you'd have to base your decision on something that happened maybe an hour ago, 10 minutes ago. It's much more useful to have something that's less precise but has lower latency, and that's kind of a key thing. I mean that's speaking really to the real-time aspect of the architecture and of the talk, is that I'd much rather have this than that. I don't care for high level precision. And so that's an interesting trade-off, because that means that if you're, as you're processing data, as you're receiving data, you're graphing it, if your processing system starts to slow down, if your pipeline starts to slow down, you can say, all right, I'll skip a bunch of points to just catch up, because I don't care of having every single point there. I'd rather make sure that I can catch up and be up to date. So that's kind of an interesting trade-off. That, of course, will not work at all in a financial application where you want to count every single money transfer, for instance. So you cannot. In our case, we can skip points. We can skip data points. And I guess I'm grateful for that. But that doesn't necessarily apply to what you guys are doing. So just having everything in one page. Constraints, so latency 10 to 30 seconds roughly, always available, highly access controlled data. The freedoms we have, at least some of the degrees of freedom we have, is I don't care about 100 millisecond round trip, less than 100 millisecond round trip, or even less than a second really. I don't care about elasticity. It's a very predictable pattern of data we ingest. And I care about precision, but that's one thing I can give away. If in exchange for latency, I can trade precision. Good? Am I making sense? Okay, cool. Yeah, do tell me if it's not, if I'm not making sense. So, having said that, I want to take a quick look at what the monitoring data, what it looks like really, from maybe even more concretely. So there are two types of events. Two types of data in monitoring, really. So you have metrics and events. And so metrics are really basically time series. So a metric could be the temperature of this room, hour after hour. It's usually it could be number of bytes processed by an interface inside a machine. It could be number of visitors to a site. It can be pretty much anything. Anything that's a time series. So, and events are just annotation. I'll show you a little bit more detail. So, metrics time series. So at the most basic level, it's timestamps and values. That's the basic representation. It has a bunch of metadata. It could be the name of the metrics, for instance, number of people in the audience. Has some context, which is meetup, data engineering meetup. The date is XYZ. Has some units. If this is number of people, for instance, it has an owner, in this case, who's measuring to whom the data belongs to, etc. That's pretty much it. I mean, in our system in Datadog, that's kind of the core data. That's the core data model, if you will. So it's very, very simple. It's very, very uniform. There's not a ton of variations. The resolution we chose is that of a second, and that's really, again, back to what I was saying in terms of it takes, at least 10, 30 seconds to interpret a graph, to be able to react to it, to understand what the data is telling you. So there's no point in measuring things at a resolution lower than 1 second. And it's adequate to capture thus signals of less than 0.5 hertz. And now, when you think about it, the way it really works, if you set up Datadog, you, for instance, deploy it on your laptop, you'll have a little program, a little agent that's going to run and collect metrics about what your CPU is doing, what your memory is doing, which program are running, and so on and so forth. That typically is going to sample data every 10 to 20 seconds. It could sample more often, but you don't want to waste cycles to measure. You also want your laptop or your server to do interesting things, useful things. So that's why, even though we can measure things down to a second, typically, if you look at graphs we're giving you, you'll have a point every 10 to 20 seconds. If you have, and this is maybe slightly, I would say off topic, but in case you want to measure higher frequency signals, you can use something called StatsD, which will pre-aggregate whatever metrics you want to send it, and it will consume that. So overall metrics, the interesting thing, there are two interesting things. One, they're pretty high signal noise ratio in the sense that if you have a very noisy metric, something that goes all over the place, it's probably not very useful in the first place, so we need to derive it to get something useful. So it also speaks to the fact that you can lose some precision and still kind of be able to understand what the metric is telling you, what the performance of the system, for instance, is. And the second thing, which is great, is that metrics are immutable. So because there's a timestamp and nobody's figured out time travel yet, we'll be able to persist metrics, and they're never going to change because they measure something that happened in the past, essentially. So quick example, if you want to measure, so IO weight is I use in this case resource metrics. So what what the machine is doing, what the CPU is doing. This is number of cycles in percentage that are spent waiting on some kind of disk, for instance. So we have, so this is an example of a query. So now the result, if you send this query into Datadog, because use case number one, graphing, we're mostly interested in displaying data. There's no point in giving you 1 million data points back if we're going to compress that to a graph that's going to fit in your screen. So it's typically 200 to 600 points for display. And these points are essentially timestamp value, timestamp value, timestamp value, timestamp value. And when you graph them, this is what you get. You can, I mean, this is something this is actually, I think, a measure on a machine. So that's something I took this morning. So the interesting thing, because graphing is one of our main use cases, the resolution isn't, the resolution is time independent. By that I mean, if you look at 1 hour data, you get, say, 600 points. If you look at 1 month of data, you also get 600 points. So there's clearly there's a time aggregation that takes place so that the system doesn't query. If you look at a month of data and you have 2 million points, we don't query 2 million points, send back to the browser 2 million points, and wait for the browser to render 2 million points. Of course, we time aggregate as we query and return to you just 200 to 600 points, so you have a nice graph. Does that make sense? So if you want to get a little bit more complex, and I want to explain a little bit also kind of some of the intricacies of time series and monitoring. Let's say you want the same metric but average across a number of machines, a number of sources, if you will. So the query is slightly different. It's not that important. The results are always the same, 200 to 600 points, because again, this is for graphing, and you don't really care about having 1 million data points to only graph 400 at the end. The interesting thing is that in this case, you get the average across a number of machines. So what we call spatial aggregation. So you basically take this, which is the metric for all the machines, and then you compute the average. So because at the end, this is what you're asking the system to produce. And so one interesting thing is that because not all data is sampled at the same time, you have to do some form of interpolation so that you can basically compute the average on the same timestamps. Does that make sense, that part? Okay, cool. If it doesn't, please raise your hand. So there's time aggregation, there's space aggregation happening. So these are examples of metrics and the kind of processing we do on them and the kind of queries you can do off them. Events are really, so this is much more simple. So the kind of stuff we collect is really time-based textual annotation. So it could be, oh, I released a new version of the software, or oh, somebody got a page because a web machine went down, or anything, oh, we started a new marketing campaign, and so on and so forth. So the data model is very simple. It has title, body, and then some metadata author tags. As an example, so here these are events. So Nagios is a sort of legacy monitoring system. We're collecting so this is the metadata is what it is. There's a title, there's a body, there's a timestamp, of course, and then that's it. It's interesting to mix events and metrics because it lets you annotate the data. Because a lot of times, for instance, let's say you start a new marketing campaign, and so if you don't know that, and you see a huge spike in your web traffic, you're like, shoot, maybe the CDN is messed up, and we get all the traffic back to origin server, and we're going to just die. Everything is going to burn down to the ground. But maybe it's actually because there's a new really successful marketing campaign that's just driving more traffic, and just the reaction, obviously, you'll be careful in both cases. But in the second case, where oh, this is because there's that, or it's probably because there's this new marketing campaign. Being able to sort of mix and match, it's really not very visible, but there are markers where I have the origin of the arrows. There are markers. It's really useful because now you have a sense of, oh, it's a brand new event. I have no idea. We're sort of in twilight zone. I don't know what's going on. Or yes, okay, this is expected, and then this is how we can react. So it really makes a huge difference from a how you react to it, how you react to your metrics. So that's it. I mean, that's the core data model in our architecture, in the problem spaces. That, and the rest is just it's not extra, but it's not that important. Okay, so now we know what kind of data we produce or gets materialized in the system. Let's look at the way they're accessed, how data flow. So in most cases, I mean, this is the simplified workflow. You have things, so agents being small machines, small programs on a machine collecting metrics, sending them to Datadog, or just so programs hitting our API. Just send data. So it gets into something that we'll call intake, gets queued, gets processed, gets persisted, and then that data is accessed basically either because you're looking at a graph via a browser, and that graph may be the last hour of data, for instance, which is very common, is you want to know what's happening now. And once in a while, you'll go back and say, oh, let me look at what happened a week ago or last month or something like that. But the vast majority of the traffic outbound, so inbound is all the telemetry, all the metrics coming from the servers and the applications. Outbound is, it's a little bit of recent data and then very infrequently kind of the more random queries. So on the intake, what that means is that, first of all, we want to be able to ingest data at an ever-increasing rate. And that means, I mean, if the business is successful, we'll have more customers. Customers have machines, more and more machines that are sending more and more metrics, and applications that are sending more and more metrics. So the intake has to be able to take more and more data, basically. And it's the kind of data, there's no partition by time. By that I mean all the customers send all data all the time. There's no, oh, today is Tuesday, I don't know, it's customer A that's going to send data. So it's not batch. It's always like constant flow of stuff coming in. The latency constraint that I mentioned about, so actually, here I have 30, 60 seconds, more like 10 to 30 seconds. So that's again, between the time the data is collected to the time it flows into the intake, it's going to be in the order of tens of seconds, not minutes, not milliseconds. And so when you have this kind of stuff, particularly when you have you're ingesting data at a very constant rate, and you have a sort of fairly sort of constant upper bound for latency, you end up basically having just a bunch of queues. That's what I'll show in a little bit. Outbound queries, it's queries, so it's different. So inbound, we send data. Outbound, we get basically graphs, for instance. So the latency there is more like a few seconds. You start, you say, show me the graph, and you want to wait for a few seconds, not for 60 seconds for the graph to display. The time span that when you query the data for, typically you want to look into, most our customers look into the last 1 to 4 hours. Because that's what I want to know, what my app is doing now, not what it was doing 6 hours ago. I mean, it's sometimes interesting, but most important is what's happening now. And the interesting thing is that, and that's maybe a little bit, so I'll explain exactly. The queries, when you look at the parameters of the queries, so there's time span, there's the metric you're interested in, and let's say the machine where it's collected. These are, when you render, when you look at dashboards that people put up of graphs, they tend to be slow-moving dimensions. That is to say, either you look at a bunch of different metrics, but it's the same time span, so it's the time is fixed, basically. You do a bunch of queries, but the time is fixed. Or you look at, typically people may look at everything coming from a single machine or one given metric across a ton of machines. So in that sense, when you do the query, there's already some sort of locality of the parameters. It's not completely completely random. And other kind of stuff that we have outbound, which I touched on, this is use case number 2, is alerts, is telling you when something goes wrong, so it's detecting anomalies. Latency is typically 60 seconds because you need, there's no point in alerting as soon as a metric shoots up across above a certain level. Usually that's not what you want, because if you have a sudden spike, you'll get a ton of false positives. Say, hey, I'm above 100. Hey, I'm above 100. You don't want that. Usually you want to know, hey, I'm above 100, and that's been the case for the past 5 minutes, or the past minute, or past hour. So depending on the case, on the use case. But for instance, let's say I mean, anything around like CPU, for instance, is a good example where you don't want to, if the spike in CPU, it doesn't really matter. You want to know, you don't want to know it, every second that something's happening. If it's, for instance, storage or some kind of memory, something that's constrained where you don't have an infinite amount of it, you want to know once you're getting close to the limit because there's no extending it. Like, if you run out of, for instance, this space, you run out of this space. There's no, you want to know as soon as possible. So that's alerts really. And the spatial aggregation, it makes things a little bit more complex when you have a bunch of different time series that come at different point in time, and makes things a little bit fuzzy, especially towards sort of the boundaries of the interval. And the last thing we want to send is events. So for instance, or when you query for events, you say, hey, give me the list of all marketing launches, for instance. And you want to wait for a few seconds, not for 10 minutes to get the results. So that's inbound, outbound, and in the middle, there's a bunch of stuff. So it's all the stages, and I'll go over them in a little bit. But basically, it's things that will, for instance, look at the incoming metrics and look for anomalies, persist them, do roll-ups to aggregations that you can have sort of constant, you can keep your latency fairly low, and do some kind of reporting. So look at data across the board and produce some reports. So the latencies, again, that we see in the middle, it varies between, if you want to resolve something right in the flow, you want to, for instance, resolve a metric name from a name to an actual identifier, 10 milliseconds. If you want to query and assemble time series, a different resolution, for instance, if you say I want to see a time series that spans a month, then it should take about a second, not more. Anomaly detection, I talked about it, typically 60-second latency or 60-second time span or latency, no less than that. If you don't want to do hourly aggregates, so any stage in the processing pipeline that rolls up hourly, then obviously it's every 60 minutes that it needs to wake up and do its stuff to compute the aggregates for the past hour. Same thing for dailies, and then if you do batch reports every week, then it takes, it's like you run that every 7 days. So the multiple latency, the only reason why I wanted to have it there is to show kind of the different time scale that exists throughout the system, and as you can imagine, so something that's disk-based 10 milliseconds is probably not a good idea. That's probably going to mean something in memory. So 1 second, that's probably something in memory as well. 60 seconds could be memory, could be on disk, depending on the volume and so on and so forth. So that's why I had that. The interesting observation also that, again, is going to drive the architecture is that the volume of data, inbound volume, is way, way bigger than the volume of data that's outbound. That's because you have, I don't know, let's say, 100,000 machines telling Datadog, hey, this is how I'm doing, these are my metrics, and then you'll have that 1,000 people looking in front of 1,000 screens, so one screen each, let's say even two, looking at 10 graphs, so that's only 20,000 queries at most, whereas one machine can generate 100 metrics. So there's a clear symmetry between how much data we're ingesting and how much data we're serving back. And that leads to some interesting sort of architectural tweaks. Good? All right, okay, so now on to the architecture. So a few design constraints or architectural constraints. So inbound, because we have so much data coming in compared to what we serve out, we want to have some durable queue, basically something that can take data in, that has a predictable intake time, so where you want to write data, persist it so it can be processed later on. It shouldn't take, the time it takes to get that data should not vary, because otherwise you're backing up at the very entrance or the very start of the pipeline, and that means your customers are backing up as well. So that means they're not going to get the data on time. And it's got to be scalable, just because I said that our sort of intake volume is just ever so, grows. And it's got to be scalable in the sense that we want to spend less money. If we double the amount of customers, for instance, we don't want to double our bill to ingest the data. We want to have something that's lower than that. So that's scalable in that sense. Scalable also in the sense that it has to consume a lot of data, but that's that. Outbound design constraints. So for outbound traffic, you want to have fast access to real-time data because people want to see what's happening now. So that's going to be the main use case. I want to see all my graphs for what's happening now. So you want to have something that gives you fast access. And you also want to have fast access, relatively fast access to persistent data, i.e. past data, for instance, where you want to see, oh, I have, 20,000 people on my site right now. How much did I have a week ago at the same time, same day, just a week ago, same time. So that's gonna live somewhere. I mean, if you have a lot of memory, it could be memory, but at some point you're gonna have to persist to something that is not memory. So you need something that gives us access to it. And internally, the kind of constraints that we have is, again, it's all queue. It's a bunch of queues, so they've got to be pretty fast. We want to have minimal coupling between the various aspects. If it's a pipeline that processes your data, you don't want to have crazy coupling because if something happens somewhere, you don't want the problem to propagate too quickly. And then we need a bunch of data stores that ranges in durability and access sort of inversely. So you can have low durability database, that is to say, the data can go fairly quickly and you may lose it, but very fast. So that's typically stuff in memory, and then you lose the box, and then the memory is gone, and then that's it. I mean, you have to find ways to find that. All the way to super high durability, that is to say, I don't care, but slower. That is to say, I don't care if it takes a second to get the data, but that data has got to be there no matter what. So because we store historical time series, and we can't say, oops, we lost the data, sorry, we're just come back later. Okay, so so adding a few pieces to the equation. So really, this is what it looks like. You get data in either typically through the API, so or the machines are sending to the API. Hey, this is how much CPU I'm consuming, for instance. There's a lot of machines acting as intake, so ingesting the data, basically storing it into either both in memory and then queuing it on disk. So the in memory, why you want to have it here is because if somebody's asking for the data in real time, you want to cut through. You don't want to read from disk what you just wrote. Rather, if it's memory, when you do a query, the web tier that's here can directly hit the in-memory storage and say, hey, I want the up to the second data, just give it to me, and it's going to be in memory. It's going to be just much faster. And because again, it's going to be a small fraction. The outbound traffic is going to be a small fraction of inbound traffic. You can play a few games to try to optimize that. So otherwise, the path is you go to queues. So stuff that gets queued up, it gets and then processed and then written to some durable store. And I'll explain which store we picked. And then there's a bunch of cataloging that happens as well. At the bottom, so all that, which we call data layer, is something that from the outside, from the web application, looks like something you ask, give me this metric between time A and time B, and it's going to return the time series. It does the magic. For instance, if you're asking for data that spans the last 6 hours, for us, some of it will be served from memory, some of it will be served from a durable, one of our data store, Cassandra in this case. And that's completely transparent. So the data layer does exactly that. It just mixes things and makes them seamless. So it's an abstraction layer, I guess. So that's really, the high level architecture. There's not a ton more to it. So data layer is really at the core is a bunch of data stores and just a bunch of glue code. There's not much more than that. When we started in 2010, there were about 2 open source sort of time series database around. There was Graphite and OpenTSDB. So Graphite it's hard to scale Graphite, definitely not to the scale that we're at. It'd be pretty hard. And in OpenTSDB, it's HBase based. So back then we were like, well, HBase, I don't really want to spend too much time dealing with it. So we ended up building something on top of Cassandra. Since there's been a few interesting open source projects on time series databases, Influx, DB, Vina from Go Circuit. So there's a number of them that are out there. They tend to be based on like level DB for storage and things like that. So if you're interested, I can definitely get into details. But that's really what the data layer is. It's not very complicated. It's just a bunch of tools. So the tools we used for that is so Redis is, as you can guess, all the stuff that's in memory lives in Redis. It's nice because we used it because it gives you very regular access to your data. So if you have time series kind of flow naturally in Redis, we use, so that's the low durability, super fast access. You have Cassandra is somewhere in the middle where it's much more durable. And Cassandra, I don't know if you guys use it or know, it's a distributed kind of key value store, let's put it that way. So it's relatively simple to operate. It'll store data on disk. It's really good at writing at relatively constant speed and constant time. So you can write a lot of data and it's not going to degrade too much. Reading is a different story. But when you're ingesting a ton of data in, it works pretty well. And I realized that I forgot one thing. The queues that we use is Kafka. So this is from LinkedIn. I don't know if you guys know what it is. It's basically a queuing system that is much simpler than most queuing systems or the ones you may be used to, like MQ series, AMQP, and so on, where it's a thin queuing layer on top of the JVM, which is on top of basically the kernel. So it's really fast. Yeah, file system. Fast, so yeah, exactly. It's really fast, and it's really good for sequential writes and sequential reads. And what we have are it's a first in, first out. Sequential writes, you get the data, you write it to disk, and then something's going to pick it up to process it. And it's not good at all for random reads and random writes, but that's not the use case here. Zookeeper, this is Zookeeper, which we use for coordination across a lot of services. Elasticsearch, that's mostly used for events. Whenever you say, show me all the marketing launches in the past week and overlay them on a graph, they're going to come from Elasticsearch. Postgres, we use it for basically storing the application, the catalog, who the users are, what the graph definition is, and so on and so forth. And then the glue really is in Python itself. So there's actually one of my teammates gave a great talk at PyData, I think it was 10 days ago, about how we use Python. So I don't know if there are Python users in the audience. Yes. If you do anything, I'm sure you know that, but we had great experience with NumPy, Python, particularly. So it's great for us. Python is great because we're very productive, reasonably productive with it. Has great library support. It's everywhere. Every machine we use has Python already. It's unfortunately not very memory friendly, so which leads us to some interesting optimization. This is the talk you wanna watch if you wanna get into the sort of the details. I'm happy to go into details on the questions as well. So a few challenges, and I think we're getting towards the end of the talk. So in terms of, just to give you a sense of scale, so it's about 30 billion data points every day that we're receiving. So it's just machines, it's any number of machines sending. In total, 30 billion data points. It runs 24/7. One of the challenges that we had is hard to monitor. So we are a monitoring company, but it's interestingly hard to monitor our stuff. So we do a mix of dog fooding plus using other tools, but yeah, I mean, I guess it's the reality of the complex sort of real-time apps these days is like the monitoring becomes, and that's why we have the business, I guess, is a non-trivial operation. One of the challenges, so I mentioned a few times, is this sort of ever-increasing amount of data that comes in, never stops, never takes a break. So that's, as you can imagine, both on the technical side, but also on the operational side, it's not easy to manage. Memory for us becomes the most precious resource. And that's just, I guess that's everybody is there, but because latency is so important, even though it's bounded at, a few seconds to tens of seconds, it can't be, it can't move much higher than that. So that doesn't give us a lot of leeway. And so when we're running out of memory somewhere, you can see it pretty quickly. in our internal graphs, you'll see stuff piles up somewhere in the pipeline. Stuff starts to grow. It's like, oh shit, we gotta fix this. So the number one game we probably play at Datadog is on top of building a new product is basically chase latency bubbles. So anything that slows down. So it's measure, and the way we do it is very simple. Is like we have a bunch of metrics. Everything is instrumented. So we find, oh, there's a jump here. Why is there a spike in time it takes to render something or time it takes to query one of the data stores? Then we basically profile the code that does that, tune it, test it, hotfix, and so on and so forth. That's a very constant operation or game that we play pretty much every single day. Something like that is happening. That's just because the system is growing. And the interesting thing that I didn't mention is when we started in 2010, obviously we didn't know if we had a business. I mean, that's a startup, right? So we wanted to have something out of the door as quickly as possible. So we started with a very naive implementation that was based on Postgres. And we knew it was naive, but it took about maybe 6 hours to figure out that we had to change it after we started to ingest some data. And so the architecture that I described, even at a high level, is really iterative. It's just basically doing this all the time. So replacing this, replacing that. We had queuing based on Cassandra at some point, which is a terrible idea, by the way. But anyway, we had it. We said, okay, F this. Then we put Kafka in, and then we had when we introduced Redis, that was in response to some bottleneck somewhere. So it's really the day-to-day is a lot of that, and that's pretty cool. Now, in general, one thing that I really like about the stuff that I'm doing and monitoring in general is that in a technical capacity, if you're engineers, then you are our customers, and that's great because that means that we interact with you guys, and then we want to make something that's useful. So that's the last thing I want to say. We are hiring. And so if you want to become a Datadog, and it took me a while to understand the joke. So if you don't know, well, I'll explain because it took me at least a month. Data is like a starter guy, and dog is Snoop Dogg. Anyway, if you want to become one of us, jobs@datadog.com. And that's it. That concludes my presentation. Thank you. So I covered maybe a lot of material, maybe too much, so I'm happy to take questions. Okay, we'll do row by row. Go ahead.
Do you ever have a customer who didn't have NTP in their metrics at all?
I will repeat the question. So did we ever have a customer that doesn't have NTP? We always have a customer who doesn't have NTP. And so what you see is they call you, or they on IRC, they say, hey, I can't see my metrics. And you look and you say, yeah, there's nothing. And then it happens that either their graphs are basically in the past because the machine is sending data thinking it's in the past, or it's in the future. So we've had cases where we look for the data and we can't see it. It turns out that the machine is not time synchronized, so it's maybe 2 hours behind or a week ahead, or so we've had the problem fairly often, unfortunately. Yeah, I guess.
So you mentioned roll-ups in there at some point.
Yeah.
I was wondering if your architecture is set up so that if a person wanted to go back, or a customer wanted to go back and query data in the past, finance resolution,
Yeah.
don't need it, by the way. Let's say they're trying to train a model for some sort of anomaly.
Yeah.
They apply the domain knowledge. Do you save it, or do you just roll it up, aggregate it?
Okay, so the question is, do we roll up? So we roll up past data, and I said we roll it up. That is to say, we summarize it so that whenever you're asking for data to graph data for the past month, we give you 200 pixels, 200 data points back, or 600 data points back, and we do that because we have already pre-computed the summaries, the time summaries. The question is, we save everything. So we save the highest resolution data, which is for us down to the second. And from a product perspective, what happens is that it's like almost science fiction. You look at the month of data and you zoom in and you see more detail. You zoom in and you see more detail until you get to the finance resolution. But so yes, that's available. Yes, absolutely. Okay, so we'll continue. Yes.
Are you ever servicing queries from
So are we servicing or serving queries or servicing queries out of more than one data store? More than one data store, yes.
For a single query.
Yeah, for a single query, yes. And that's simply based on the time boundaries of the query. So for us, the past 4.5 hours, I think, are in memory. So if you ask for 6 hours, the start is 6 hours ago, end is now, we'll still serve the last the last 4.5 hours out of memory. Partly because the processes down the pipeline that are supposed to persist the data may not have flushed the data yet. So you go to Cassandra where you store sort of intermediary data, maybe it's not there. So that's why we stitch the data on the fly when we query.
What's hard about that?
What's hard?
What's hard about it that you have to deal with?
Mostly because, I mean, the main thing is in Python, for instance, you have to use numpy. I mean, it's not particularly hard, but you just have to you have to time align the array. So at the boundary, when you stitch it, you have to make sure that there's enough overlap so you don't have a gap, for instance, between stuff that's served from memory, stuff that's served from disk, that kind of stuff. That's a fairly well understood problem for us. Yeah.
So if you double your customers, you don't want to double your costs.
Yeah. So that works. That's a great question. I need to be able to answer it. So the question is how do we not double the cost of operations while we double the number of customers? So in what I showed, the raw intake is not necessarily the bulk of the expense. I mean, the bulk of the data is actually going to live in storage, and so that grows reasonably linearly, but we can compress it. The bulk of the processing scales relatively non-linearly because for one thing, we optimize the code, and we do what I mentioned that we said we're doing is that we replace pieces as they get too slow. So that's basically the idea to keep a fairly high gross margin for the business. Yeah, behind it. So why? And I also mentioned. I forgot to mention S3. So Elasticsearch, how do we use Elasticsearch? We store, if you remember, let's see, events like this stuff, where you have like textual annotation of the data. We use Elasticsearch for that. Watch out for the size of the indices. That's the main thing we've had. So Elasticsearch as such works great. It's like Postgres. It runs out of the box. You don't have to really watch it until you realize that shit, there's a problem, and then you missed something. But that's because you're so busy with the rest that there the pieces for us that are so Elasticsearch, Redis, Postgres. They run almost on their own. Cassandra is getting there. S3 definitely runs on its own. And the thing I wanted to say about S3 is that because you remember that I said our data is immutable, being passed data, then S3 makes a perfect case for that because it's we never need to like randomly seek and change a little bit here and there. Yeah, all the way behind, and then I'll just circle back. At this point, it is running on AWS, yes. It's like zone distributed and so on, but yeah.
How do you find the original EBS, or are you just using S3?
So EBS, we still use a little bit of EBS. It's kind of shitty. It's very bursty. I'd say in general AWS. So it's a great way to start. That's not where we'll end, but that's that. So at EBS clearly. Actually, I may have had I blogged about it a while back, but if you read the fine print, they give you, even if you get provision IOPS, which is like a reserve stuff on AWS, the fine prints are fairly interesting, where they'll guarantee performance of how fast you can read and write only in X% of the time, and only if you read and write within certain boundaries. So, I mean, it's hard. It's definitely a hard problem, and I think they're doing a great job. But it's still not as good as like SSD. It's not sometimes not even as good as SSDs on my laptop. So, yeah. Yes.
Yeah. So I was going to ask, like, remember when AWS went down?
Yeah. Yeah. Yes, we did.
Oh, nice. So was that your previous data? I'm curious how you access that.
So, so the truth is I don't even know because this because the thing I obsess about is how much data we're receiving, and so that hasn't really changed. I mean, there was a dip actually. There was some dip, but we couldn't see much. But how much data we're serving, I don't really care. I mean, the marketing team and I care about the product as it's used, but otherwise, like I wouldn't know.
Yeah, I would have thought everyone would like go to Datadog right away.
Yeah, so which leads to some interesting development for us in the near future, kind of getting partly out of the US.
Can you talk a little bit more about your queue, how you digesting your messages in the queue, particularly how you're monitoring the processes that actually consume the topics of content, and how you're synchronizing with probably
Yeah. So the question is how we monitor. So the queue system we use is Kafka. It has a concept of topics, which is places you write to. How we monitor the writing to the queue and the reading from the queue. So we basically we have workload metrics, which I mentioned the amount of work being done. So our processes are reading from the queue to do something, and in this case to roll up or to do anomaly detection or stuff like that. So the metrics that we'll watch is how many points have you consumed, for instance. And so that means reading a bunch of messages from Kafka, opening them up, seeing how many points there are in each message, and so on and so forth. So we don't really have, interestingly enough, a great sort of native Kafka instrumentation. We did it kind of above that layer. Just we care about if we basically if there's a drop in throughput, so in the number of messages you're reading, assuming the messages entering the system are constant and it's a drop there, then usually we'll look at how many messages you're consuming and also what the machine in terms of I/O is doing, and that'll basically tell us a story. If there's a lot of more I/O than before, then Kafka is having some issues.
Yeah, but it doesn't tell you what happens if the worker crash, and then like how are you monitoring the thing that's actually digesting?
So they themselves feed metrics into Datadog, and so we have also alerts that will tell. And the alerting engine, I didn't get into that. The alerting engine runs kind of on a given schedule. It like every right now it's every minute it wakes up, just looks at everything and say, okay, everything's fine, or everything's not, or there are things that are not fine. So that part is independent from queuing. If there's no data making to it, then for instance, if in front of it or some things that are feeding it are not producing anything, then it'll tell us, hey, you're not producing any, the producers are not doing anything. So then we could say, okay, is the producers not doing anything because they crashed? And we monitor all of them at once, so we can know, oh, this guy crashed or restarted. Or is it because something else? So that's usually just the starting point of the investigation is, oh, we're expecting to receive X amount of data points per second, and we only got 60%. What's the problem? How many processors were running? Does that make sense?
Yeah.
Okay, cool. Actually, all the way to the back, and then I'll come back. Yeah, sure. The Bitly link is here.
What version of Kafka are you using?
I think we're on 0.7. We're deeply thinking about 0.8, but yeah, but and also we want to. I'd like to have other people test it in production. I mean, beside LinkedIn, and not find out that. So the failure modes so the queuing system has some replication built in the newer versions, and the question is, so we don't use that yet. I'm a little bit cautious about what the failure modes are going to be, because we give some backdrop. We were also relatively early users of Cassandra, and I've kind of been there, done that. So I can wait a little bit. Yeah.
So you said that AWS went down, you didn't lose any.
Yeah.
Right. So I'm kind of curious. So you have this. You're doing a global routing at the wherever level for things, and then so let's say you lose a data center. So you have that 4.5 hours in Venice.
Yeah.
You're replicating that across available. So all.
Yeah.
So
yeah.
how does that work?
So we have, I mean,
Venice in a row.
So yeah, so we replicate data. So depending on the data store, so Cassandra has built-in replication, S3 yes, Postgres yes, Kafka yes with some caveats. I mean, we do it manually basically. Redis has it also with some caveats, but so what we yeah 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 we try to have everything everywhere as much as possible. So yeah, the question was how we survive the AWS outage, and knock on wood. I mean, there's that's.
So is yours, are you processing in your other ones? So you have like a Redis master, and then you have a REPL set, across the country.
Yeah.
Which is Redis.
Yeah.
AWS, right?
Yeah.
So is that live, or is that just in case?
So that at this point, it's mostly in case there's a problem. So that's to the 10 to 30 seconds. It has happened that the shit hit the fan, as it were, and then we need to failover, and then we didn't automate every single failover scenario because it's really damn hard to conceptualize ahead of time what's going to crash. And so in that case, you're like, oh damn, it's going down. So what you see if that happens, is you'll see the graphs exactly what I was talking about earlier. And the kind of trade-off I don't want to make, you start seeing this. And because the data is just not, it's arrived, but it's not being read, consumed. And so that's when this is like major crisis mode for us. And we try to keep those as singular as possible. Other questions? Yes. It's typically I think it's 30-ish thousand or 40,000 machines reporting roughly. How many machines we need for that? We have about, I don't know, maybe of various classes, but we have maybe 100 machines at this point. Yes. So behind you. So question is, how do I shard the data, or how do we shard the data in Cassandra? So in Cassandra, I love Cassandra to write data. So we use Cassandra to persist data for, let's say, about a week. The sharding is done by, so there's a key, which is the metric name, the account name, and also the general time frame you're looking at. And the way we do it is we TTL all the rows. So after 15 days, the data is going to disappear from Cassandra, no matter what. Because otherwise, before we had that, we had a ever-growing Cassandra cluster, and then it becomes impossible to delete data. And that's when we said, okay, fine, we'll stop that cluster, just move all the data to S3 and start a new one that TTLs. So that expires data after 15 days. And that keeps also the footprint of Cassandra relatively small. Otherwise, well, anyway. So and SSDs, always SSDs. Yes. Yeah. Yeah. So yes. So anomaly detection. So the question is, do we automate anomaly detection? At this point, we don't really, and the reason is, so you're instrumenting your app fairly consistently, you have thousands and thousands of metrics, while a lot of people want to buy, hey, I want anomaly detection, you'll tell me whenever there's a problem somewhere in my data, you'll alert me. In reality, right now, what people are interested they have a few key metrics in mind, and these are the ones they care about. These are the ones that their bosses care about, and so on. And that's really where they want to be alerted. How much false positive you will have when you turn on like full anomaly detection, and there's a number of algorithms for that. That remains to be seen. So we haven't implemented it, partly because people are not there yet, I think. So yes. Yeah. Yeah. So it's VPN. Yeah. I mean, like it's AWS, so there are issues some time, but it's not, you know, it's decent. I mean, I wouldn't, yeah, so, yeah.
How do you manage the consistency?
So how do we manage the consistency between the data stores? So we have deltones everywhere. We basically inject known signals inside the pipeline, and then when we check everywhere that we're expected to see them. So we don't not only check that we expected to see them, that they're there with the right value. For instance, we have, I don't have it, but we have a Batman series that sort of draws the top half of Batman and bottom, you know, like the sign, the bat sign. So we check that as you inject it in the system, and it should appear somewhere down the pipeline. We also check that it appears on time, so that you inject the signal, and within, you know, top 60 seconds, you can read it out. If not, that means there's something that's delayed in the pipeline. Yeah.
Can you talk a little bit more about when you give us position for previously,
Yeah.
you're skipping to the tail of the queue, or you're just downsample on your...
So we're doing, so the question is, what do we do when we trade off precision for latency? We skip points. Basically, we'll skip, for instance, every, you know, we'll skip 10 or 20% of the points. So we don't do that normally, but sometimes it's necessary. So that's one of the levers we have to always try to stay there, is to skip it. And the truth is, because you know, again, it has a fairly high signal noise ratio, the trend is still there. You're losing points. It's not, you know, it doesn't really affect your ability to decide. Much less so than if you have like a Barney graph and you're like, you know, what's going on? You know. Does that make sense? So we have instrumented. We have basically you run a command line. It starts for a given account, starts dropping every 10th point of what we're receiving for a given metric or something like that. Yeah. Yeah. So we have a number of functions to graph performance data. So we have a histogram. So we can produce some histograms. You can derive, integrate our basic arithmetic, moving averages, and so on and so forth. So kind of the traditional time series operators that you'd apply. We're adding more and more, time shifting, counting, stuff like that. Cool. Oh, one last.
So do you predefine metrics so I can say these are, like, it's not all collect you.
So the question is, do we predefine metrics? The answer is no. You just say, here's the metric name, here's the value, here's the timestamp, here's the value, and that creates a metric. See?
But you also read system stuff, so that's
yeah.
done automatically by the...
Yeah, whatever agent we have, yeah. So the system stuff, so if you try Datadog, you'll say you run it on your laptop on your server, you'll get like some metrics out of the box, like anything around consumption, so resource consumption. But you can also produce your own metrics, which usually the more interesting stuff is you send your own metrics about your application, because like, you know, CPU, it's interesting, but not that exciting, and not that actionable actually. So we'll also let you send whatever metric you want, basically, as long as it conforms to a time series. That's the gist of it. Cool. All right, thank you very much.